All right, so I did not get your exams graded because Mondays I teach till 4, and then I have something I do at 6, and then I was out of day. So I will have those graded for you tomorrow, and we'll go over them tomorrow. So any questions on other stuff before we jump into a new topic? I think it's good. Thank you.
I saw you post the program yesterday. I'm trying to get it done like yesterday, and when it's actually got actually
Which program? Oh, yeah, okay.
But when it's actually exactly how that.
Yeah, the server starts at 8 in the morning. Yeah, so everybody looked at the ODP?
So I could try to set what's giving me a Java socket order.
Yeah. Yeah, it should be up now.
It wasn't that bad, though.
Yeah, a bunch of people had it done before 9. Well, not a bunch, but a few. So yeah, let's talk about hashing first, and then we'll take a look at the ODP towards the end, because it'll probably make more sense after we talk about why we're doing this. So yeah, the subject this week is hashing. So hashing is associated with associative arrays. My secret. Thanks. So associative arrays, we touch on these in Bash. We touch on them when we talk about awk. The idea behind an associative array is it's like an array that we're used to dealing with, but instead of indexing the elements with integers, we can index the elements with anything that we want. Strings or floating point numbers or executable files or pretty much anything. So imagine an array where the indexes are names. So there might be an index Nick, and there might be an index Carol, and there might be an index Izad. And this array might be called jobs. And the element indexed with Nick tells you what Nick's job is, which is, computer science. And Carol's job is mechanical engineering, and Izad's job is electrical engineering. And this is a really powerful way to store information, because if I want to know what Carol's job is, I can just say, show me jobs, bracket, Carol. And that element will be the string ME. Or it could be, an integer, or it could be a sentinel node on a linked list, or whatever else, right? But the associative part is that the indexes we're using to access the elements of this array are not just integers. An array is kind of like an associative array, except we always use integers. They generally start from 0, and they increase by 1 until we get to the index of the last element. It's a very rigid set of indices. With an associative array, we have flexibility on what these indices are going to be. And the associative part is that in some sense, this piece of information is associated with this index. So these things we can think of as keys, and these things we can think of as data. So inside an associative array, each key is associated with some piece of data. Now we can do this with plain old arrays. We could make an array called names, and we could make another array called job description. And these could be indexed with integers. And this might be Nick and Carol. and Izad. And the job descriptions would be the corresponding. And now if you want to find what job Carol has, you simply look through the names array until you find an entry that name matches Carol. If that's index 1, then you look in the job description array for index 1 and you find the corresponding job description. So these pairs of arrays that we keep in sync with each other, this is how we do this in, say, 121 or maybe in 224. But with an associative array, we have better efficiency because we don't have to search. We can just say, give me the element with this index, and out pops the data associated with that key. So that's the setup. That's what we're after. Okay. The way that we implement this is generally with something called hashing. So how do we build an associative array by ourselves? Well, take a plain array. Some number of elements in it. And we need what's called a hash function. And our hash function is going to take some key. And it's not going to give us the data. It's going to give us an integer index. And in this plain old array, at that index, we will find the data associated with that key. So what might a hash function look like? Well, let's pick on our homework problem. So we'll make an array of 31 elements. And let's say that our hash function is going to be the sum from I equals 0 to number of characters, ASCII code of key bracket I, all reduced modulo 31. So this is your ODP. We'll look at it in a few minutes. But basically, if you come in with a key like Carol, we want to take the ASCII code for each of those 5 characters, add them together, and then reduce that sum modulo 31. That will give us an integer from 0 to 30. And whatever integer it gives us, that's where we're going to store the data associated with this key Carol. Make sense? So I can cheat because I have a function to do this. So Carol will hash to the index 1, which means at this location, I'll store the job description for Carol. Yeah? Absolutely. So or Caller, some mythical character. So Caller is also going to hash to index 1, which means that I would try to take the data associated with this person and store it right here. That's going to be a problem. Okay, so we'll deal with that in a second. So let's just throw some other data in here. So Nick's going to hash to 17. So Carol goes to 1. Nick goes to 17. Izad will go to 20. So in an ideal setting, these mappings are unique. And if I want to know what Carol's job description is, I take the key Carol, I add up the ASCII codes, I reduce mod 31, I get a 1, I come into my array at index 1, I find ME, I'm done. And at some level, it doesn't matter if I have 31 things in my array or 31 billion things in my array. The number of things in here doesn't affect how many operations it takes to retrieve the piece of data associated to a key. You take your key, you add up the ASCII characters, you reduce mod 31 or mod whatever, and that's where your data is stored. So in theory, this is an order 1 system. Order 1, remember, is nirvana. Order 1 means that the time it takes to run your algorithm is independent of the size of the data. And theoretically, we could have 1 trillion things stored in this hash, and to pull one piece of information out takes a fixed amount of time, independent of that trillion or billion or whatever. It depends on the length of the string, but if our strings are no longer than 10 characters, then it's, 13 operations or something.
Well, wouldn't it not depend on the length of the string? Because as you increase the size of the data, the time it takes, the number of operations of the hashing operation is still the same.
It's still the same, right? But
We're talking about what the changes in the size of data.
right, yeah. He was talking about if you have a very long key, it'll take longer to hash that. Yeah, well, so you mod 31 each time that you add. If you do that inside your running sum, then you'll never overflow. But yeah, so this order of complexity is referring to the number of things in the hash as opposed to the size of the individual keys. So order 1 is nice, right? We can store something and we can retrieve something in a fixed amount of time regardless of how many things we have stored. That's way better than an array, right, where to insert or to search, we certainly needed order n operations. And if it was sorted, we needed order n operations to insert or delete. And a linked list is still order n. A binary tree will be log n. This is order 1. Okay, this is as efficient as you can get. But there's a wrinkle, which is Carol and Kaylor will both hash to an index 1. And so if we get this other person, we can't store their information in this system. We either have to overwrite this, in which case we lose Carol's data, or we say we can't store you because someone's already in that position. And neither of those is a good option. So this is what's called a collision. A collision happens when you have 2 different keys hashing to the same value. In other words, when our function f fails to be injective. 2 different things mapping to the same point. So non-injectivity gives us a collision. And it's a problem. So let's work with integer data because it's easier to spin examples like that. So let's store student IDs in a hash. So here's going to be my hash function. F of n is just going to be n modulo 10. So that's always going to give me a number between 0 and 9, and I'm just going to store the student ID and name at that location. So here's our first student. And that's going to hash to index 4, right? If we reduce it modulo 4, so this is going to go right here. And it's going to be Bob. And we get our next student who's 94045 9876. And that's Tina. And so that's going to hash to an index of 6. So we'll store that information there. And we'll throw myself in there. So we take the student ID, we find modulo 10 is just a 5, so this is where the next one goes. All right, so along comes Izad. Let's do 3, 4, 3, 4. All right, so you hash that through your hash function, you get a 4, it wants to go right here, this place is already occupied. All right, we've got a few options how to handle this. Collisions are inevitable, okay? Unless your table is big enough to hold every possible key that you might want to store, you're going to have collisions. Student IDs are 8-digit numbers, 9-digit. 9-digit numbers, so unless you have like 100 billion or 100 million or something entries in your array, you're going to have things that collide. So one option is to use something called chaining. The idea of chaining is instead of actually storing our piece of data here, we store a pointer to a linked list. And now the first thing that maps to index 4, we store that in the first node of the list. When we get something else that maps to that same index, we add that to the list. And so we're doing a combination of a pure hash and just using a linked list. Now, it's very efficient to insert. If we insert at the beginning, that's a fixed number of operations no matter how long that list is. But our search time is going to suffer. So suppose that all of these things are pointers to nodes. So Izad would get stored at this next location. And now if we want to look for Izad, we hash the student ID, we get a 4, we come down here, and now we have to start moving down the list and look for Izad. And so that will grow in time requirements as the number of things that we have associated with each index grows. So it comes back to something like an order n, depending on how many collisions we're having. But it's an easy way to implement a solution to these collisions, and it's not bounded. Our list can grow until we run out of memory. And so if we have a lot of collisions, this algorithm won't break, right, assuming that you have memory left in your system. Your ideal is to avoid collisions as much as possible. For example, if we're using student IDs, this would be a really bad hash function. Take your first 3 digits and use that as an index. Okay, that's going to be horrible here at Clark because the first 3 digits are almost always 940. At another school, that might be a great algorithm. Okay, same with the middle 2 digits. So if you understand the nature of the data, you can make a better choice maybe about how you're going to hash these things. But you're still going to have collisions at some point. Okay, so chaining is one way out. Let me show you another way. So we'll stick with the same hash function. We'll just reduce some number modulo 10. Let me just store numbers in here so I don't have to keep writing names. So f of 45 equals 5. So if I wanted to store 45, I'd put that right here. And f of 34 equals 4. So that'll go right here. Now suppose I want to store f of 115. That's going to map to a 5, and location 5 is occupied. So here's what we do. Something called probing. So we extend f, extend the hash function to take 2 arguments. So we want f of a key and something we call a probe. And our probe is going to be an integer. And the idea is the first time that we try to hash our key, we're going to use a probe of 0. and it's going to tell us where we should store our key in our table. If there's already something there, we're going to rehash with a probe of 1. If there's something at that location, we'll hash again with a probe of 2. And we'll keep doing this until our hash function gives us a location that's not occupied. You got that? So it's like poking a stick in a bunch of holes until you find something where there's nothing in there. And that's where you put your thing that you're trying to store. So our probe starts at 0. We hash our key. If we get a collision, then we probe we hash again with a probe of 1, and so on. So here's an example: f of key, comma probe equals key plus probe modulo 10. All right, so when the probe is 0, this is just going to be the same as our original function. Okay, but when the probe's non-zero, it's going to do something different. So we want to store 115, f of 115, 0. This is 115 plus 0 mod 10. That's a 5. There's a collision. So we reprobe f of 115, comma 1. That's going to be 115 plus 1 is 116 mod 10. That's a 6. We look in here, location 6 is free. That's where we store our data. How are we going to retrieve it? So now you want to fetch item 115. You hash it with a probe of 0, you get a 5. You look at location 5, that's not your data, but that spot is occupied, which tells you that if you had tried to store 115 after this was occupied, you would have gotten a collision, and you would have stored it with a different probe. So we rehash with a probe of 1. And we find a 6, and we check index 6, and it's not there. I mean, it is there, so that's our entry. Now, if we try to find the number 135, we'll hash it with a probe of 0, get a 5. It's not at that location. But this is not empty, so we'll hash it again with a probe of 1. That gives us a 6. It's not at that location, but that location's not empty either. So we've got to hash it again with a probe of 2. That gives us a 7, and there's nothing in that location. Now we know 135 is not in our table. Because if it was, it would have gotten stored either in location 5 or 6 or 7. Yeah. Yeah, it's all overhead. And it gets worse. Yeah, you could make a find an open spot function that probes successively until it finds an opening and then returns the probe value. Is that what you're saying? Yeah. Returns the index value? Return the probe value. Yeah, you can do that. But this is still what's going on underneath, right? You're probing successive locations. All right, there's a few problems with this. So the first problem is, if I want to store the number 24, it's going to hash to this. That's going to be a collision. When I probe with 1, it's going to hash here. When I probe with here, it's going to hash here. When I probe with a 3, it's going to finally succeed, and it'll store my 24 here. But my data is tending to like cluster up. I've got all this empty space around here, and my data is all gathering around here. Right? This would be a problem, for example, if we were hashing student IDs using those first 3 digits. And they'd all be 940s, and the first time we'd store it at 940, the next time we'd store our data at 941, then 942, and so on. So it can be nicer if your probe function doesn't just go linearly. So this is called linear probing. But a better probe function might be something like this. Take your key, but add the square of the probe. So your first hash attempt will go to some location. Your next hash attempt will go to the next location. A subsequent hash attempt will jump down 3 spots. A subsequent attempt after that will jump down 5 spots, and so on. And it will tend to spread out the data the more times that you probe, which will hopefully, in some cases, stop the data from clustering all around popular key values.
But that's skipping, like couldn't it potentially like just hit values over and over again?
It's possible. So there's some science behind picking a good hash function and a good probing algorithm. There's also some number theory behind choosing how big you want your table to be. If your hash table, which remember is an array, right? If that has a length that's a prime number, you're generally going to do better. Because if you were to try to store something every 5th location, and your array has a length of 10, you're only going to get 2 shots. Right, so let's go back to picture of our array. And suppose my probe function was to take our key plus 5 times the probe number, modulo 10. Well, if I try to store at 4 and I get a collision, I'll add 5, I'll try to store at 9, I'll get another collision, say. If I add 5 times a probe of 2, it's going to bring me back to 4, and then back to 9. Right? And you're just going to bounce back and forth between a small set of locations. If the length of your array is a prime, that's not going to happen. Any distance that you decide to move, you're going to have to go through all the possible locations before you repeat. So you can toss some number theory in the mix and get better behavior. So some science to picking probe functions. There's some other complications here. So let's see what can happen. So let's use quadratic probing. So we're going to hash integers, and our hash function will be that integer plus the square of the probe modulo 10. Okay, so we'll start off with store 15. Probe is 0, 15 plus 0 is 15, modulo 10 is 5, so this is where our 15 is going to go. Store a 20, that's going to get hashed to a 0, so that'll go right here. Store a 25. That'll collide with our 15. So we'll add a probe of 1 squared is 26. This is where the 25 will go. And then 35 will collide on the first probe value of 0. So we'll add 1 squared brings us to 36. That's a collision. So we'll add 2 squared. 35 plus 4 is 39. This is where the 35 will get stored. All right, now we want to search for 35. So hash it to a 5. There's a 15 there, but it's not empty. So move on. Hash with a probe of 1 brings us to 36. That's not the number we want, but it's also not empty. So probe with a probe of 2, and that's 39. There's our 35. So it finds it. Okay, now delete the 25 from our hash. So take 25, hash it with a probe of 0, we get a 5, that's not 25. Hash again with a probe of 1, 26, modulo 10 is 6, there's our 25, so delete that. Mark it as free or something. Now let's search for 35 again. 35 mod 10 is 5, that's not our number. Rehash with a probe of 1, 36 mod 10 is 6. Location 6 is empty. If we're not careful, we're going to say 35 is not in our table. even though we deleted 25, we need to remember that there was something stored there. So that when we try to do a search, if we find a collision at location 6 with something that used to be there, we know we have to keep probing. So we would say, okay, there's nothing here right now, but there was. That could have caused a collision. Let's probe again. So now we probe 35. With a probe of 2, that brings us to 39, modulo 10, location 9. There's our number. So we've got some complications now. When we delete, we need to somehow keep a flag around saying that this was occupied with something, as opposed to a location that's never had anything stored in it. And when we search, if we hit a cell that had something in it but doesn't anymore, we need to keep probing. When we're inserting, though, so if we want to store 105, hash it, mod 10 gives us a 5, that's occupied. Probe 1 gives us hash 106, mod 10 gives us a 6. Come here. We had something there, but it's been deleted. We can store our 105 right here. So we need a few pieces of information in each location. So we need to know if that element in our array is in use. We do need to know if it's been deleted.
Would it be feasible to move everything down after you delete?
That's hard to do because it's possible that what was here was 105, or it might have been something that ended with a 6. And this hash function's pretty easy to reverse, but if this was adding up strings, right, then it's I'm not sure it's well defined, but it's certainly time consuming. And assuming you're not getting many collisions, it's probably preferable to do this. But it's an interesting theoretical question, I think, of can you go back periodically and compactify your hash table. I'm guessing there's some systems that actually do that, particularly if this was something that was going to run for months and hang out there forever. Another option would be to simply periodically go through all of the data and rehash it all. Right, so just march through here and create a new hash table storing these things. And that might be a cheap way to compactify, depending on how much data you have. But you know, it's something you can do in the background. While customers are coming in and hitting this hash, you can be building a cleaned version of it, and then when it's done, just switch over to that one. Yeah?
So could you, say, make a 3D array and have 3 separate hash functions?
Mm-hmm.
Produce, like, and then use each one to get a unique index?
So if you collide on the first one, go to the second one.
No, just always use the 3 different hash functions to get the 3 different indices.
Yeah, you can do that. I'm not sure it's fundamentally different, though.
If you use 3 different modulo stuff.
Because a three-dimensional array is really just a one-dimensional array. And you index, you know, first index plus 1,000 times the second plus 1,000,000 times the third or something like that. So I think you could get the same behavior with a single dimensional array and just combine your 3 hash functions to do the index dereferencing. But that's a nice way to think about it, is just using different dimensions and come down with your first hash, go over with the second, go back with the third. That's pretty cool. So yeah, that's valid. Nice. All right, so what does a hash look like? As an abstract-ish data type. So initialization, you need some way to create an initial hash, which will be empty, presumably. You need some way to store a key data pair. You need some way to fetch based on a key and return whatever data is associated with that. Maybe you want a separate search function. give a key and it tells you whether or not that key is stored in your hash. But you might actually be able to do that with your fetch. You could just have your fetch return null if it doesn't find the key. But maybe that's an expensive operation if your data is very complex. So maybe you want a separate search function. The stuff you store in a hash, right, we're doing integers or strings, but it could be anything. Okay, it can be any binary entity, which is basically everything in a computer. It could be an entire linked list. It could be a hash table. It could be a tree. All right, so this notion of a key and a data are kind of generic types. Don't just think integers. Here's the other thing you need. When we have an array indexed with integers starting at 0 and going up through n, it's pretty easy to pull the data out of that array. You just make a for loop for I equals 0 to n minus 1, and you just grab array bracket I, right? When your array is indexed by things like Nick and Carol and Izad, how do you print all of the data that's stored in your associative array, in your hash? We can't make a for loop that says, you know, for name equals Nick to Izad, right? Because that's not well defined. And most names that we could think of aren't going to be associated with some data in this structure. So in the case of associative arrays, we need a way to somehow pull our data out without knowing ahead of time what all the set of keys are. And this is going to be a recurring theme, especially in 223, when we start working with packaged things that, that don't just associate the data with consecutive integers. So we need something like what we'll eventually call an iterator. And here's a typical way that you can do an iterator. We can say, give me the first key, where the ordering is not well defined, but there is a first key, and we can say, give me a subsequent key. And we can loop on this call to next key. And we saw this with for eaches inside bash and in awk. So first key is something that gives us one key that's associated with something in our hash. And after we call first key, every time we call next key, we get another key that we haven't already seen that's associated with some data in the hash. So inside a loop, we can keep calling next key, and each of these keys that come out, we can use that inside, say, a fetch to pull a piece of data out. And there's some way for next key to tell us there's no more keys that you haven't seen. Maybe it gives us null, and then we know that we've gone through the entire set of data. So traversal of hashes is not something we can do without having access to something like an iterator, because we don't know what the keys are. Now, if we know that this hash is implemented using an array from 0 to 9, right, we could go through and we could check all of those valid flags and the deleted flags, the in-use flags, and see which of these entries in the array have a piece of data, and we could print out the data. But that's not an abstract data type of viewpoint. That's looking at the implementation details. So this is basically a way to be able to get inside that structure and pull out the pieces without having to go inside and understand how the hash is implemented. So in C, there's a way to do this. There's a package called DBM, was its original name. It became GDBM, which is GNU DBM. DBM is short for Database Manager. And it's a series of functions that you can call to do these kinds of things: store, fetch, first key, next key, and so on. And so let me just give you an idea of this just as an example. So there's a gdbm.h, which sets up a bunch of symbols for us. There's a database file, which has a type of gdbm file. So that's kind of like file star when we do fopens. There's a new type called a datum, which is a structure with two pieces: a pointer to your data and something that tells how many bytes are in your data. Okay, again, this is very general purpose. So if you want a string, Your datum.pointer would be the address of the first character. Your datum.size would be the number of characters, probably including the null terminator if you don't want to get into trouble. So this is the initialization. This opens a database. You give it a name. This is actually going to be a file on your hard drive. And then the way that you want to open it, I want to open it for reading and writing. And if it doesn't exist, I want to create it. And the other values are kind of boilerplate. So this is saying create a database file in my current directory named database. That's where this hash is going to be stored and maintained. If you want to store some data, you set up the D pointer and the D size pieces of this datum, which is called key. So this is just demo code. So I read a line from the user, store it in buffer. I set D pointer to point to the first character, and I set D size to be the number of characters, including the null terminator. So I add one to the string length. And then I get a piece of data that I want to store, and I store the D pointer and size for data. And then here's the store command. So I pass the name of the database DB, the key, the data, and then a flag that says, if you don't find this in the database, store it. If you do find it, replace it. So your key is only found once in the hash, but I can change the value by just restoring. Okay? Nothing to do with collisions here, right? Collisions are not part of the abstract data type view of a hash. Those are implementation details. This is a perfect hash function to me. This will take whatever the data is and associate it with that key inside this database, which I'm storing in a file called database. And if you want to retrieve data, I ask for a key. I set up a datum key with a D pointer and a size. And then I just say fetch. Tell it the name of the database, tell it the key that I'm looking for, and it returns a piece of data, which is a datum. And the flag from fetch is that if the size is 0, it didn't find the thing in the database. So if the size is bigger than 0, I can print out the data. Otherwise, I'll say the key is not found. And then here's the iterator. So I can say, give me the first key from the database. So GDBM first key retrieves the first key. And I can fetch the data associated with that and print it out. And the next key, I tell it the key that I just got, and it gives me another key. And I just keep repeating this until the key that it comes back with has a pointer of null. And that's how it tells me it's out of keys. And then, yeah, I forgot to mention the deinitialize. So GDBM close does the reverse of opening the database. So we also want some kind of deinit. So you compile the usual way. You do a -l GDBM that links it in with the GDB library. And so I can store any data pairs that I want, any data key pairs. So let's store something. Let's do Izad, and he's an EE instructor. And let's store Nick, and I'm an art teacher today. And let's store Carol, and she does ME professor. And let's store Tina, and she does nerd girls. And now I can retrieve information, so let's see what Nick does. Nick's an art teacher. And let's see what Barney, the purple dinosaur, does. Barney's not found in the data. And we can use a dump command, so D, and it'll go through and it'll show me all the information that's stored in there. And the order is effectively random, right? When you use an iterator, generally there's no guarantee on the order in which you get your data. It's possible, in fact, that if you do this twice, you won't even get the same order. But it's guaranteed to give you every key exactly once before you have any repetitions. And one of the nice things about GDB is that it stores this database in your directory.
What do you mean by repetitions?
So you won't get the same key twice.
So it is possible to get the same key twice?
Using an iterator?
Yeah.
No. Yeah. I think I was being over emphatic there. Yeah, each time that you call it, you'll get a new key, which will be different from any key you've already gotten. And then eventually it'll give you some indication that you're done, you've run out of keys. But in some cases, if you keep calling it after that, then you might get the same key again. So database is a binary file. It's mostly gibberishy, but it's persistent. So if I come in here and I say, let's see what Izad does. He's an EE instructor. So you can use this GDBM as not only an efficient way to store and retrieve information because it's a hash, but it's also persistent across runs. So you can store information, exit your program, come back the next day, and it's still stored in there, which is kind of nice. Associative arrays are like one of those ultimate hammers, right? Where once you sort of get your brain around what it does for you, everything can look like a problem that's solvable by a hash. Okay, they're really easy to use and misuse, and I spent a couple of months just using associative arrays for everything when I first encountered them. At the time, I was writing a lot of compilers and interpreters, and imagine you're trying to write something like an interpreter, something that takes in code and executes it as a program. But one of the things you have to do is keep track of variables. So the first time you encounter a variable, you look in your hash of variable names, and if you don't find it, you store it in there and you associate a value of, say, 0 if you're going to initialize. Next time you encounter it, say you're asked to add 1 to this variable named x17, you go into your hash with x17 and you see if it's in there. And if it is, you can pull out the current value of that variable. You do your operation to update it, and then you write it back into your hash. And this is your symbol table. It's keeping track of all your variables for you. And your variables can have pretty much any kind of name, but that doesn't bother you because you just go into your hash and you say, show me the data associated with this name, and there's the variable value. And if it comes back empty, it's a new variable, and you know it's uninitialized, and so on. So this is a really useful kind of way to store and retrieve information, and very efficient in an ideal setting, depending on a lot of factors. All right, so any other questions on that? So tomorrow we will go over your midterm and we will discuss PA4, which I will post tonight, and you can start working on whenever you're done with PA3. And we don't have class on Monday, remember, because Monday's a holiday. So I want to go through that before then. All right, I will see you next time then.